Oi, BRAINLM, a foundation model for brain activity recordings. Cool paper today. Basically, they took all of that cool new science happening over with large language models like ChatGPT, and they applied it here to neuroscience, fMRI, brain data. And they said, what can we actually do once we have a big model capable of predicting future brain states? A lot of really interesting stuff happening with they can basically, it seems like, do neuroscience without having to actually mess with your real brain, and they can just kind of take a bit of easy brain data and fMRI from you, and they can do experiments and learn about your brain from this model's predictions of what your brain would do in certain conditions. Real cool stuff. I suppose let's get into it. Before we start, remember to like, subscribe, comment, share, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, support me either through Patreon or YouTube. For as low as $1 per month, you can get early access to my videos, or for a one-time payment, hit my Venmo. And if you'd like to borrow my brain for an hour or two, book a consultation call. All links are over on my Linktree. Let's get started. So, you're probably familiar with fMRI, functional magnetic resonance imaging. It measures blood oxygen level fluctuations that reflect regional neural activity. This is, I believe, the most commonly seen photos of brain scans you'll see. Blood oxygen level hopefully corresponds to some sort of activity. I'm not very much of a neuroscience person at all, obviously, but we're going to be dipping our toes in the water here today. And regional activity, as in it can look at what different parts of the brain are doing in terms of their level of activity, right? However, it's usually pretty difficult to deal with and to learn anything from. Signals that are blood oxygen level dependent, we'll shorten that to bold, represent an indirect measure of brain function, right? So it's not to say that it's perfect or anything, but in theory, the brain areas requiring or demanding more oxygen, I suppose, should be doing more stuff. And beyond that, it exhibits really complicated spatiotemporal dynamics, meaning it changes a lot over time and just across the brain regions. It's not exactly something that we humans can just look at an image of and know what it's doing. The brain's very, very complicated, obviously, and this measure is somewhat indirect. So these researchers trained a model on data sets of fMRI recordings. They have two data sets, one of which they took 80% of it, called the UKB data set, and trained off of it. It was 61,000 recordings. Notice here, as opposed to most prior research, is has very, very small amounts of data and therefore just is really only useful for its specific scenario. Whereas what they're doing here is they are trying to actually pre-train, as in show the model a large amount of relatively general data that we can then somehow use later for specific tasks, right? So we took that UKB data set, took 80% of it, trained off of that for 61,000 recordings, and then we had a held out validation set, right, of that data set with 20%, as well as a full separate different data set. This is interesting here is, so a lot of time machine learning, you'll take your whole data and you'll split it into most of it you train off of, then a small portion, 10, 20%, you hold off and you test on it to make sure the model hasn't just memorized everything. And that's all well and good, but they have an extra issue here in the fact that these fMRI data sets are so frequently so different from each other that it actually made sense to keep an entirely different data set held out as a separate test validation data set. Because there are differences not only with, like, I'm not sure the exact specifics of how that works in the neuroscience, whatever fields, what the machine is, kind of thing, and how it was recorded. One example is I believe the actual frequency of the recordings of the was different among these two data sets. They're pretty close, I believe, but there's still a different frequency. And so they wanted to test if it generalizes across two different qualities of that different data sets, right? And the way they kind of look at this involves segmenting the brain into a bunch of different regions and then tokenizing those regions. So here we have 424 brain regions. Now, the actual architecture of the model that they trained on all of this brain data was a transformer masked autoencoder. So very similar to BERT, for example. The difference between this and and what you usually see in terms of like ChatGPT and stuff is every part of the data in the given recording, the given sequence, can look at all other parts of the data, and then they just mask out, hide small portions of it, and they get the model to reconstruct those hidden parts. And that's how it learns, is through the task of reconstructing what it's not allowed to see. They take those original 424 brain regions and use those to actually define their token embeddings. So they take that raw data of each one of those regions and they use some sort of mechanism to turn those regions into actual vector embeddings. Now, this model was relatively small. We have here a model dimension of only 512, which is interesting. I'd love to see how this scales up with larger data sets and larger models into the future. And if you're curious, the actual ratio of what percent of the actual brain regions get masked out is either 20%, 50%, or 75%. I forget what they did multiple. I assume it's a hyperparameter search that they'll analyze later and see what works the best. Now, here's the actual utility in doing something like this, right? Because as it stands, this pre-trained model we've just described really only works to further predict future brain states when you put in some pre-existing brain data, right? Which might be interesting, sort of, kinda, but like it's still not interpretable, so I don't know what to do with it, right? What you want to do, the reason why you pre-train a model on massive amounts of data is so that you can then have downstream applications in which you fine-tune that pre-trained model for a specific task. And they did so to have it predict clinical variables from fMRI recordings. So they don't actually want the recordings, the fMRI data itself. They want to predict clinical variables, such as is that person anxious or depressed? Are their eyes open in this recording? So therefore, are they seeing something? Is their visual cortex on? Stuff like that. They have another separate set of variables they want this pre-trained model to be able to act as the foundation upon which predicts those other variables. And they do so by appending a 3-layer multi-layer perceptron and just using a regression loss to target all of these variables such as age, neuroticism, do they have PTSD, scores on anxiety disorder metrics, stuff like that. Now, how do we actually use this? That first use earlier was just, okay, if we have someone's brain data, we can now use that regression head to predict things about them. That's all well and good, but realistically, doctors, I don't believe, actually want to record brain data and then just feed that into a large model and get out an answer of are they depressed or not, right? You can do that with regular questionnaires, and it's only approximating those depression questionnaires and whatnot we already have. So it's not really like useful in and of itself. What they do instead, the actual thing of interest in this study, is what they call in silico perturbation simulation. So they introduce a novel prompting approach that is made to elucidate the model's representation of brain dynamics, right? This technique simulates the effect of perturbations of small messings with of the neural activity patterns in a completely computational and zero-shot manner, i.e., the model was never trained on perturbation. So they are going to create this new thing that we will see how it's useful in a second, where basically they define a perturbation function, G, right? And G has parameters, and it takes as input the actual fMRI brain data, and it modifies that fMRI brain data, right? So this function G, this model G, is going to be trained to take that initial regular brain data and modify it. What we're going to train it to do? So when we take its output, G's output, that is called the perturbed sequence. It is going to be fed into the pre-trained BRAINLM. So G's a separate model from our original BRAINLM, right? We feed G's output, our new perturbed sequence, into BRAINLM, and we optimize theta, aka G's parameters, to minimize the distance between the predicted state and a target corresponding to a cognitive condition of interest, right? So we already have BRAINLM, and BRAINLM can take in any fMRI data and predict stuff like, along with using its MLP extra head on top, it can predict stuff like, oh, age or depressed or not, anxiety or not, PTSD or not, right? So when we put in the input, we put this perturbed input, aka the input from this perturbation function G into BRAINLM, it is also going to output predictions for things like age, depression score, etc., right? What we do is we say, okay, we are going to keep BRAINLM frozen doing the exact same thing it's used to doing, right? And we are going to take G, which makes the perturbed input, and we are going to optimize G's parameters such that whatever the initial predicted state that came out of BRAINLM from the initial data, we want the perturbed data to create a target, to create an output, age, depression score, whatever, corresponding to some target of interest, some cognitive condition of interest, right? So we are training G to take raw regular brain data, mess with it until it creates new brain data, edited brain data, perturbed brain data that when gone into BRAINLM, has BRAINLM predict, say, depression or no depression, whatever our interest is, or anxiety or no anxiety, right? And so now we can look at what exactly G does to the initial data. How does it change that initial data? It gives us new data. And in order to get these final target output of yes depression, no depression, whatever we're training for, right? So then by analyzing those optimized perturbations, by analyzing the new data that G creates and the difference in that new data between the original actual regular brain data, we can identify which fMRI features are most influential in altering the model's predicted brain states. So we can look at how the new perturbed data differs from the original input data, and whichever things change the most, we can presume must have a lot to do with that final cognitive condition of interest. So if some little piece of that new brain data is very different and that new output is now high depression scores, we can assume that that area in the brain that G changed quite a bit has to do with depression. So this doesn't actually reveal the data itself. This reveals insights into relationships learned by BRAINLM, because BRAINLM is powerful, right? It can predict future brain states, and it can predict all of these metrics like age and depression and whatnot. But by doing this perturbation setup, we can actually learn what features, what insights the BRAINLM itself has learned, right? So we can tease out what it has learned. Now, this does have problems in the sense that what we're doing here is very reminiscent of adversarial perturbations in a way. Is we are trying to get the model to create a model, a function G, such that we get a certain output out of BRAINLM. And we know that these models, especially one this small, like 512 is model dimension, right? We know these models in general across all modalities can be very susceptible to adversarial perturbations. So this is a bit like just creating an adversarial perturbation machine and assuming that it learned uh, good, useful perturbations that actually do make sense. When in reality, it might be the case that whatever G finds to do might actually just be taking advantage of the imperfect structure of BRAINLM. We can't know that from this study. That is an area for future work. As for the results of BRAINLM during pre-training and how well it performed, right, on the original data set it was trained on the test split, it averaged an R squared score of 0.402, which, if you're used to like physics, sounds absurdly low. If you're used to psychology, neuroscience, that's very respectable. 0.5 is like peak of what you could want. Of course, 1 is perfect, 0 is nothing, right? Or I guess 1 or -1 are perfect and 0 is nothing. But a 0.4 is pretty damn good, indicates strong generalization on unseen recordings in the same distribution. And they did find that of those different masking ratios, 75% gave the best performance of all those ratios. And they also found that it generalized pretty well to the entirely separate data set, with its R squared score being 0.361. So definitely a drop from 0.4, but still, it definitely did learn something. And again, that's pretty good given the fact that this other data set has different cohort, different details of how they got the data, different machines, different frequency of recording, all this stuff. That's pretty good. Here is a little diagram of what's actually happening in this model. So up top you can see is what the raw data looks like. It is all individual strains of time series data, each series corresponding to a different parcel, a different region of the brain. And there were, I want to say, 400 of them. And then what they do is they are going to actually take bits of this data and just mask it out, aka erase it, right, and have the model reconstruct it. So how they do that, if you look at the blue piece, they take their original data, obviously put in the form of a actual tensor, and then they have random masking, which I believe is along the spatial dimension, and then future masking along the time dimension. After mixing those together and adding in embeddings for spatial and temporal reasoning, because again, these models, attention mechanisms, right, don't actually know the difference between like different places in time and different points in space or anything. You have to give them that time positional and space positional encoding, right? Then you throw that into your transformer encoder, and then finally you can throw into your decoder, get the actual predictions for all of the pieces that were masked that were hidden out, and you can fill in the gaps in the data, and that's how it learns from any place in the data to reconstruct any other part of the data, and therefore gains good understanding representations of what's actually happening in said data. We can also see in terms of the results that we do get BRAINLM, especially in the very, very short term, has better accuracy, lower error in forecasting those future brain states. Now, when we look at the actual self-attention weights, that can show us insights about what the model is actually learning and thinking and looking at, right? And importantly, what we want to see is we can look at all of those little parcels, those places in the brain, and see what we know them to be based off our decades of neuroscience stuff, and see, okay, in a given scenario when the brain should be paying attention to this brain region, is it in fact doing that, right? And we do find indeed it works. Task recordings exhibited greater visual cortex attention compared to resting state, aligning with the visual stimuli presented during tasks. So resting state, I believe they have either just the white ceiling wall thing in front of them or their eyes are closed. Whereas during the actual recording, we do get there is a visual thing in front of them for a lot of these experiments, right? And you would expect if there's interesting visual stuff in front of them with their eyes open, that the visual cortex should be firing, right? And we do find that the model itself is all of its self attention weights are attending to the parcels, the areas in the brain that are located on the visual cortex. So it is aligning with our preconceived notions of what should be happening there. Another example is that attention patterns between mild and severe depression have more weighting on frontal and limbic areas for severe versus mild depression, right? Which is apparently what we also expect if you're a neuroscientist. I don't know. And we can get full on mappings from the brain LM from its parcel areas. I'm not going to go through them all, but basically on the right here, we have different colors corresponding to actual different brain regions of importance that they were able to tell from the experiments did align with whatever the conditioning experiment was. So kind of re-deriving what they already know and therefore verifying that brain LM is learning what it should be learning. So this brain LM provides a powerful framework for biomarker discovery. By fine-tuning, brain dynamics can be decoded to predict clinical variables and psychiatric disorders better than baseline models. This could enable non-invasive assessment of cognitive health using resting fMRI alone. So the implication here is that we might not have to actually do experiments and things to test cognitive health. We might be able to actually just like take a resting state fMRI, a very simple person just lies down in the machine, fMRI is done, and use that to assess the person's health rather than having to show them scary images or anxious causing images or whatever it is, right? It also means we might be able to figure out how to actually learn more about the brain and what causes what in the brain in a completely in silico manner, aka completely on the computer, as opposed to having to actually poke and prod and zap the person's brain. And future studies should be trying to incorporate fMRI data with other types of brain data like EEG. Don't leave yet. If you got this far, you're going to love this video or this playlist. Don't forget to like, subscribe, comment, hit the bell, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, and consider supporting me monthly either through Patreon or by hitting that YouTube join button down below. For as low as $1 per month, you can get early access to my videos. Or if you're a one-time payment kind of person, hit up my Venmo. And if you want to borrow my brain for a bit, consider booking a paid consultation video call. All of those links are over in my link tree. And yeah, end of video.